Hi there. Welcome back to my introduction to the STL. This is part 5 of an ongoing series. Parts 1, 2, and 3 covered the STL sequence, associative, containers, and smart pointers. And in part 4, we covered the foundations of my Nurikabe solver, which is a puzzle. Watching part 4 is definitely a prerequisite for part 5. This will make no sense otherwise. So if you haven't seen it, go back, watch part 4. Today we're going to look at the member functions of my grid solver in detail, see the processing that it does. We've already seen the overall data structures that it's using, and the techniques that the solver uses in order to figure out the entire grid in just a matter of milliseconds. Let's look at the constructor real quick, because this uses regular expressions, which is something neat that was added in TR1 in 2008 SP1 and into 2010 as part of the STL itself. So when I'm given the width and the height and a string containing the cells in my grid, first I need to make sure that the width and height aren't completely bogus, so I make sure that they're 1 or greater, because that's the minimum possible size. Now here I'm going to throw a runtime error exception if they're invalid. Runtime error means that it's not a programming bug, it's something went wrong at runtime, like network connection down or invalid input, that sort of thing. Things that cannot be expected in advance but have to be dealt with. I could throw a more specific exception, but for the purpose of example, I like to use runtime error. Then I want to initialize my mcells data structure. This is the 2D grid that stores each cell, its state, and a shared put region that we saw. Because I know width and height are valid, I'm going to resize it. What this expression does is mcells is a vector of subvectors. I'm going to have width subvectors, and then each subvector needs to be height tall. So what I'm actually representing it as is this is mcells here, and each subvector is a column. This is simply so that I can say mcells xy. Because I want to put xy here and not reverse them, then the first coordinate needs to be width long and the second one needs to be height long. So that's what I'm doing here. And then I'm going to initialize every element of my grid to be unknown state and to have no region at all. It's important that I do this now because subsequent parts of my constructor are going to assume that the grid has been initialized to unknown. Then I'm going to parse my string. Now, I could write a parser pretty easily that handled single digits, but it's possible for Nurikabe grids to have larger numbers. For example, 14 or 24. And the way that we would write them in ASCII is with multiple characters. So it's possible for multiple characters to map to a single cell in the grid. Now, of course, I could write a parser by hand, but it's easier to get regex to do that work for me. So I'm going to write a regular expression. If you haven't seen this before, STL's regex uses the same syntax that Perl does. It's actually derived from Perl through another standard ECMAScript. So if you're familiar with regular expressions, this should make sense to you. What I'm saying is that I'm going to parse my string, and the things that I care about are digits 1 or more. That's this part here. And so if I see a 7 or 14, this will match. Or spaces, those are unknown cells. I also need to recognize new lines because those are going to break my rows, as we saw at the part 4. And then finally, I want to detect invalid strings. It's always a good idea to validate user input because users type in garbage all the time. In fact, it's more surprising when they don't. So if we detect any characters that aren't a digit, space, or new line, we want to be informed of that. Then I use regex iterator. I mentioned, actually I don't think I mentioned, there is a whole book on TR1 and in particular regex called the C++ Standard Library Extensions, a tutorial and reference by Pete Becker. This is sort of the definitive TR1 book, and in particular, it covers regex exhaustively. It's a great resource. One of the things that regex has is regex iterator, and what this means is it can be used for a lot of things. It can take a string and iterate through every occurrence of a regular expression in that string. You can think of it as a more powerful version of tokenization. So I'm going to iterate through my std string, and every time that the regex matches, I've got cell of my grid. So I'm going to push this into a vector int. Later on, I'll transform this vector int into my two-dimensional data structure. So if the first chunk of my regex match, this is the first thing in parentheses, I've got digits. So I'm going to convert whatever match there from a string into an integer. The C++OX function s2i from the string header will convert an integer into a string and then push back that into v. Now, if for some reason the user types in a zillion that is too big to fit in an int, s2i will throw an exception. That's actually what I want here, because I'm making my grid constructor throw exceptions whenever it encounters something invalid. And so I push that back in my vector. If the second capture group of the regex match, that's the second thing in parentheses, I've got a space. I know that means unknown cell, so I'm going to push back a 0 into my vector int and do something with it later. If the new line matched, then I know that a row is ending. I don't want to push anything in my vector. It's simply serving as a boundary, so I'm going to do nothing. Now, if none of those match, then I know I've got an invalid character, and I'm going to throw a runtime error complaining that s must contain only digits, spaces, and new lines. So at this point, I've got a vector of all of the cells, but I don't know if I got the right number. I was explicitly told the width and the height, the vector should have width times height number of elements. So if I don't say the right number of elements, I'm going to throw an exception. Now, at this point, I've realized that my grid is well formed, and I've got the right number of elements, so it's okay to transform it into my 2D data structure. So I care about their coordinates, so I'm going to do iterate over x less than width and y less than height, and I need to access a particular element of my vector. What this expression means is that because we read in the string like this, I need to take the x coordinate plus y times the number of whole rows that we've parsed. That's what the expression x plus y times width is. That's the only place it'll occur, because this is where we're transforming this sort of linear string into the two-dimensional data structure. Then if I find that the int was greater than 0, I've got a numbered cell. I need to do something special for numbered cells. First, I'm going to make sure that we don't have adjacent numbers. If I parsing a grid and I see two numbers orthogonally adjacent, then I know that the grid is malformed. There's no way that can be solvable. So I'll throw a runtime error. Then I need to start initializing my data structure. So I mentioned in part 4 that I have a helper function cell xy that goes into my vector, pair, state, shared putter, and extracts just the state at xy. I'm going to use that everywhere because typing that whole expression is somewhat annoying. And I'm going to set it to whatever number I found. Like I mentioned in part 4, I can convert explicitly integers into states with a cast, in this case a static cast, saying, I know this is an int, I really do want to make it an enum, so I cast it to a state. And then I'm going to initialize a region. So the helper function add region takes position x and y and adds a new region for this cell. So suppose that I'm parsing this 2 here, I'll get a shared putter to a new region marked with a 2 that has its coordinate and the unknown cells that it's surrounded by. This is why it's important to initialize the grid to completely unknown before starting out, because if those states are garbage, then add region will do the wrong thing. The reason why I'm mentioning that is because I forgot when I was writing this program and was confused until I realized that I needed to initialize all of the states. And then finally, I initialize my mTotalBlack data member. As the comment explains, when solving a Nurikabe grid, what humans will typically do is see, okay, would this black region be isolated from this black region? I'm going to fill in these as black as usual. If this cell were white, then this black region here would be isolated from the other ones, so the cell above it must be black. That's actually a little harder for a program to do. It can do it, but you need to write a little bit of code. It's actually easier to count cells. This is a little cute trick. If you take the whole grid, width times height, in this case it is 10 by 9, and then you add up all of the numbers that occur here. Every number is a number of white cells that's going to be in that island. Then the size of the grid minus the sum of all the cells is the number of black cells that will be in the solution. So we build up mTotalBlack accordingly. We construct it to width times height at the top of the constructor here in the initialization list. And then every time we encounter a number, we decrement mTotalBlack accordingly. So at the end of the constructor, we know how many black cells will be in the solution. So when we look at this region and we ask, okay, do you need to expand? Instead of trying to determine whether it would be cut off from other black regions, we can simply say, okay, you're a black region of size 1, and I know there's going to be a lot more than 1 black cells in the entire solution, so you do need to expand, and you do have a single liberty. Okay, you must expand. So this actually makes our solver easier to do at a very little cost of bookkeeping. And then it's going to print that it's okay to go and begin solving. So let's take a look at solve. I'm going to go pretty quickly through each form of analysis. Again, I encourage you to read the code in full to see what it's doing. The first thing that solve does is it looks for contradictions, because this could be called recursively, and in order to look for hypothetical contradictions. So if somehow the grid is messed up, like we've got two numbered regions adjacent to each other, or we've got a pool of 4 black cells, we need to find that immediately. So that's why I say we should do this first. We call a helper function detect contradictions. And if something is wrong with the grid, or we know it's unsolvable, we're going to print that out accordingly and return. If we get to this point, we don't see any immediate contradictions, so we might be done. So now we're going to check if we're done, and if we are, that's great. We're going to print out that a solution has been found. So there's a couple ways to do this. What I want to do is we're done if there's no contradictions and every cell is known. So I could do a 2-dimensional iteration, and as soon as I find an unknown cell, set a bool outside. But I thought I'd use lambdas here. It actually turns out to be almost an equivalent amount of code, I think slightly less, and I don't have to go create a whole bool. So I have a lambda function here. Lambda functions are small, unnamed function objects that can be given to STL algorithms, but they can also be used at local scope, or in this case, in an if statement. So I'm going to iterate through my grid for width and height, and if I find an unknown cell, then we're not done. I return false. If I get all the way to the end, then I can return true. And so I construct this lambda, and then I immediately execute it and test it. And so if this lambda returns true, then hey, I'm done. So I'm going to print that I'm done and return solution found. So perhaps this is a little more complicated. I thought that I would demonstrate lambdas here. If you wanted to use just a loop and then a bool and then a test, you could certainly do that. Then if I don't have a contradiction and I don't have a solution, then I'm going to try to see if I can prove any cells of the grid to be either white or black. So what I'm going to do is I've got a couple sets of coordinates, pair int int, called mark as black and mark as white. The form of my analysis, as I mentioned, solve is a huge function, not that huge, and whenever it determines cells to be white or black, it inserts their coordinates in mark as black and mark as white, and then processes them, going to iterate through these sets, and then mark the cells appropriately, print out a message to the user. The reason why we don't mark cells as we're analyzing is because that could interfere with our analysis. It's pretty easy to get confused. It's much better to do it as a separate pass. So the simplest form of analysis, actually a bit about that, the way that solve is structured is it tries simple things first and complicated things later. It wants to do the cheapest analysis possible early on, so if it can prove some cells that are white or black easily, then it'll return, okay, I marked some cells, keep going, before doing very complicated analysis that takes a while. So it's arranged in order of increasing complexity, not only for ease of presentation, but also for efficiency. So the first thing that it does is it looks for complete islands. So as I mentioned, we can iterate through all of the regions using our set of shared putter M regions in linear time. So I'm going to use a for loop. We've seen how to iterate through sets before. And what M regions is a set of shared putter to int. So the iterator is a, set of shared putter to region. And the iterator is going to be a set of shared putter to region : iterator. When I dereference that once, I'm going to get a shared putter to region. When I dereference it again, I get the region itself. Here I do want the region, and I don't want to have to say dref I, or alternatively, I would have to say dref I arrow, which is what this is helping me avoid. Instead, I'm going to just construct a reference, and then I can say r dot to talk about the region. That's all this is doing. It's a notational convenience. So r is a const reference to a region, and then I'm going to ask, okay, is this region numbered? And if it is its size, which is the number of cells that it currently contains, if that's equal to the number that it's marked with, then that region is complete. So I'm going to take the unknown cells that it's surrounded by and insert that into my mark as black set. So a couple things here. When I ask our size, this is calling the size member function of the region's internal mchord set. And a set knows its size in constant time. It's just stored in a field somewhere. And then when I insert the unknowns that this region, complete region, is bordered by, it might be empty. For example, if I've already proven that this region, if I've already detected that this region is complete, and I've marked its cells as black, then Afterwards, the set of unknown cells that it's bounded by will be empty. It's okay to insert an empty range into another set. It'll do nothing. In fact, I could test whether there were no unknowns, but it would be almost as, in fact, I believe as efficient to simply let insert detect that, oh, these iterators are equal, I'm going to do nothing. I certainly don't believe that that will be a performance bottleneck, so in the interest of minimizing code, I'm going to just insert the unknowns into my set mark as black, even if it might be empty. Then I call a helper function called process that takes a bool saying whether to print out anything, these mark as black and mark as white sets, and then a string to print out. What process will do is if it finds any coordinates in the mark as black and mark as white sets, it will update the grid accordingly, print out a message, and then return true. So if process returns true, then we found something, and then we're going to return our keep going status or contradiction found if for some reason we encountered a contradiction like trying to mark a cell repeatedly or fusing two numbered regions. Usually that will be keep going though. So we can look at the output, and we start off with a clean grid, and then of course we're going to detect that some islands are complete. In particular, there's an island of size 1, so we initially have a complete island. We mark the cells around it as black, and we highlight them appropriately, as I mentioned, and then we print it out. So where is this information coming from? This is coming from our constructor. When we constructed grid, for every numbered cell, we constructed a region for it that was marked with the cell's number and its unknown cells that was bounded by. In this case, the ones region was a region of size 1 with one cell in it, bounded by 3 unknown cells. That region was detected to be complete, and then here are the unknown cells. So that's how this information is coming to us. We mark them as black, and then we proceed on. So afterwards, we're not going to find any more unknown regions for the any more complete regions for the time being. So we're going to proceed to the next step of analysis, and that's looking for regions that have to expand. In this case, the cell in the lower left must expand northwards, upwards, because otherwise we would have an isolated black region, a black region that's too small based on the number of black cells that we know we're going to have. So the second step of solve, and I could have broken out each of these chunks of analysis into separate member functions. I believe actually that would have cluttered up the source code. That's why solve is so big. Of course, your style is up to you. If you want to use smaller member functions, then go right for it. So the second form of analysis that I do is I look for regions that are not complete yet, but they have only one unknown cell. And thanks to my region data structure, I can find this very efficiently. So again, I iterate through the regions, and I'm partial if I'm a black region and my size, the number of cells in this region, is less than the total number of cells that I know must be black. Or if I'm a white region, that is a disconnected white cell. I'm just going to mark a cell up here as white. If I'm not yet joined to a number, I must expand in order to eventually meet up to a number. It is invalid for a Narakabi grid to have an isolated white cell that's not connected to any number. So if I'm white, I don't need to look at my size. I know I am partial. Or if I'm a numbered region and my size is less than the number I'm tagged with, then it's partial. So I'm storing this in a const bool just to simplify my code, make it easier to read. If the region is partial and the size of its unknown set, so the unknown cells that it's bordered by, is exactly equal to 1, then I know that I need to expand into that cell. So if the region is black, then I'm going to insert that unknown cell into mark as black, or if the region is not black, meaning that it's either white or numbered, then I've got to mark that cell as white. Here I've determined that the size of the unknown set is exactly equal to 1, so I can get my unknown begin iterator and dereference it, because I know the set contains one element. So if I find any cells that can be marked as black or white, then I'm going to print out that I expanded these partial regions and proceed accordingly. What I'm doing is every time I pass through this chunk of code, I'm going to expand all the regions that I possibly can once. So it's possible for me to expand both a black region and a white region, and so I'm going to get a teal highlighted cell and a yellow highlighted cell. And then as I iterate through, maybe I can expand those again. I could have written the program so that it would keep trying to expand regions all in one pass, but I believe that that would have cluttered up the output, and I don't believe that it would make it any faster to run. So that's why it's very methodical and does everything only in one step. So that's why I expand this partial region. Now after this, I can't run either of my two analyses again. They're going to find nothing to do. There's no complete islands. There's no regions with only one liberty. So I need to proceed to the next step. And if you read Wikipedia, if I find something like, here's the grid edge, and I find a 2 cell in the corner, then I know that the 2 has got to go either up or right. Either way, the cell in this corner here opposite cannot be white. If this cell were white, then the 2, if it expanded northward, would be an island of size 3. And same if it went this way. And if it didn't expand at all, it would be confined to a space of 1. So when I see this construct, then I know that the cell must be black. This also occurs in other cases. If you read Wikipedia, what the most general form of the analysis is that if I have a region of n-1 cells, so it's got to get exactly one more cell, and it has only 2 liberties, and those are diagonal, then the cell that's opposite from them must be black. In general, I'm trying to write my analysis as general as possible so that it's applicable in the widest variety of cases. So even though I could detect regions that are exactly size 2, I would want to phrase it in the form n-1 so that it can be applied in more cases. In this case, it's only going to be applied for regions of size 2. Here I've got a couple 2's that are on the corners, so I know that the cells opposite from them must be black. Here I've got a 2 cell. It wasn't initially in the corner, but I've proven that the cells below it must be black. So it has only 2 liberties. These are the only 2 unknown cells next to it. And because it's an n-1 island, this one must be black. So that's why it's appearing here. So if I look at my solver, what it does is it iterates through the regions again. As we can see, we're using the same construct over and over. Having these region data structures makes the solver so much easier to write. And then if the region's numbered and it's an n-1 island and the unknown size is exactly equal to 2, I can determine all of this in constant time. Then I need to figure out, do you have 2 diagonal liberties? So what I do is I get the coordinates of its unknown cells. In this case, I know the unknown set is of size 2, so it's okay for me to dereference the begin iterator and increment it and dereference it again. If their x coordinates and y coordinates, if their absolute value difference is exactly equal to 1, then I know that they're diagonal. So in this case, I'm handling a bunch of configurations here. It could be that I've got the 2, I'm just going to say it's a 2, and here are some cells that are known. It could be that the liberties are like this, and here is the cell that's not part of the 2, or it could be that I've got some cells here, and the 2 is here, and this is the far cell. I could write special case code, but it's easier for me to handle all of it simultaneously. What I'm doing is, if I've got these 2 unknowns, I know what the unknown cells are. I'm going to call this one x1, y1, and x2, y2. The cells that are on the other diagonals are, this is x1, y2, and this is x2, y1. I believe I've got that right. One of these is part of the region that we're analyzing, the 2 or the n-1 island, and the other one is the one we're interested in. So I can ask my region, do you contain a particular set of coordinates, in this case x1, y2? If I do, then I know the other cell, x2, y1, is the one I'm interested in, or vice versa. Now it's possible for this far cell to already have been proven black through other means. So only if it's unknown do I want to insert it into my mark as black set. It could also have been already marked white, in which case we've got a contradiction and we'll discover that. So in that, when all of this is done, I found these n-1 islands and blackened the far cells. So the overall thing that you should be seeing here is that thanks to using things like vector and shared putter and mostly set, I can write my analysis in high-level terms talking about the problem domain. I'm very concerned about regions and coordinates and that sort of thing. I'm not concerning myself with updating reference counts, allocating memory, walking through red-black balanced binary trees, none of that. All of that is being handled by the STL, allowing me to focus on what I care about, in this case, solving this puzzle, which is ridiculously hard. So those are the n-1 islands. Now the analysis is getting more and more complicated. At this point, I need a new form, and that's to find unreachable cells. What I call unreachable analysis covers a couple things. First is cells that are too far away from any island to ever be marked white. The other kind is cells that are adjacent to multiple numbered regions. Unreachable analysis actually covers both of them. And while I could have dedicated code to find cells that are adjacent to like these two threes, it's easier just to let unreachable analysis do it for me. In fact, unreachable analysis is so powerful, it even handles complete islands. Because once you have a complete island, the cells next to them can't ever be marked white. I do have a separate pass for complete islands, partially to show you how to write the simplest form of analysis, but also because it simplifies the output. I had taken my solver and removed that complete island analysis, and the output was somewhat harder to understand because whenever it said unreachable cells blackened, it could be running complete island analysis, or it could be finding these what I call forbidden bridges, or cells that are too far away. It's easier to do it in separate passes, for humans to understand, at least. So this is actually getting to the point where it might be marking cells that you don't immediately see as a human must be either black or white. So it's instructive to take a look at these and understand what the solver is doing. So let's take a look at the upper right of this grid here. Here I've got the 2s. Actually, maybe I'll just sketch this larger. I've got this here. Here's a 2, and over here is a 2, and nothing else here. N-1 analysis has already proven that this cell must be black. So this subchunk of the grid is what we're looking at for unreachable analysis. And what it's doing is it's proving this cell here must be black. How is it doing this? Well, let's try to figure it out for ourselves as humans first. What if this cell were white? Okay. Now, we can't have an isolated white cell. It's got to meet up with a number. How can this cell meet up with a number? Can it go left? No. Because if this cell were white, we would have an island of size 3, and this island is of size 2. So it can't possibly go left. Can it go south? No. Because again, we would have an island of size 3. Can it go right? Nope. Now it would meet up with this 2 and have an island of size 3. It has no way to escape. So this cell is actually unreachable. We can think of it in other terms as when we have cells like 2s here, they control the unknown cells next to them. So if the region needs a certain number of cells that this cell would add too many to connect to the island with, then it can't step on these controlled areas. So this cell must be black, and that's why unreachable analysis is marking it as black. Similarly, perhaps not so similarly, when we have adjacent numbers like this, say I've got these 3s here, could this cell be white? No, because it would join these 2 numbered regions, and we know that that's forbidden, so this cell must be black. Unreachable analysis naturally handles this case as well, which is why I don't have a dedicated separate pass for it. In earlier versions of my program I did, but it was superseded, as my comments indicate. The cells over here in this L configuration, they're being marked as unreachable for the exact same way. They can't meet up with any numbers. They would form 2 large islands with these 2s. And these cells here are also unreachable because they can't meet up with the 2s, and they can't meet up with the 3s because it would expend at least 4 cells to get over there. So unreachable analysis is correct here. In fact, we're seeing that the program is almost kind of smarter than we are as humans, which is exactly what we're looking for. So how does unreachable analysis work? This pass is complicated enough that I have a helper function to do it. I also use it elsewhere. So because I'm going to call it twice, I don't want to repeat that code. So I iterate through all of my cells, and if a cell is unreachable, I'm going to mark it as black. We'll see how unreachable analysis works in a bit. Then I'm going to do, let's see what happens with the HTML. So I've blackened those unreachable cells. Now I can run earlier analyses because my grid has been updated. So this 2 here is now surrounded by 3 black cells. It's got to expand north. This 3 has got to expand south, and so forth. So that's why these are expanding. Oh, we found a complete island. This 2 is surrounded. It's doing all the forms of analyses that we've already seen over and over until it reaches a stopping point. And in this case, here's the stopping point. None of the analyses that we've seen so far will allow us to make progress. We need a new one. And this one is somewhat easy, but the reason why I've postponed it in Solve to this point is because we're going to use unreachable. One thing about NERC hobby is that there can never be pools of 4 black cells. So when we see an elbow, an L configuration like this, we know that the cell in the other part must be white. Because if it weren't, then we would have a pool of 4 black cells. There's a second, more complicated form, and that's over here. So let me sketch this. So if we have, in this case, it's a 3 cell, and it has a line of 3 black cells above it. And it has some unknowns. And this one over here is black. And the one above it is black. Okay, this is what we care about. So here we don't have any elbows of 3 black cells, but there is a potential pool here. Imagine if this cell were black. So I'm just going to fill it in. Okay, then would there be a pool? Yes. Because this unknown cell is now isolated. There's no way it could be white because it could never meet up with a number. It's surrounded on all sides by black. So if this cell is black, this one must be black as well. Uh-oh, we've got a pool of 4 black cells. So when we see this configuration, if we imagine one cell to be black and that causes the other cell to be unreachable, now we're using the same analysis, then we know that that first cell must be white. This is actually mentioned on Wikipedia, and we're going to implement it in a very natural form once we've got this unreachable helper function. So I'm going to iterate through my cells. Here I've got a slightly unusual form because I care about what I call squares of 4 cells. I want to iterate through x from 0 to width minus 1 and y from 0 to height minus 1 so I can look at these squares of cells. This is valid for me to test because if I happen to be on a 1 by 1 grid, then width minus 1 will be 0. Same for height minus 1, and I won't do any iteration at all. So what I want to do is I want to look at 4 cells and see, okay, are you 3 black and 1 unknown, or 2 black and 2 unknown cells? So there are many configurations that this could be in. For the L cells, we could have an L like this, an L like this, that's not an L, L like this, L like this, and with 2 black and 2 unknown, they might take this form, they might take this form, they could be above, they could be below, they could even be diagonal. I run this for diagonal cells because it's possible for this form of analysis to succeed, and it's actually more work to try to avoid doing it here. I want to handle all of these cases uniformly rather than special casing everything. So I have a helper struct here that stores coordinates in a state, and I'm going to use an STL array. This is the array header that came from TR1, and it's an array of XY states, and its size is fixed to 4. I don't need to use vector here because I know I'm looking at groups of 4 cells. It's not going to expand. But I would like to use the member functions like begin and end of the array, std array, rather than using a built-in C array. So I'm going to store the coordinates that I care about in this block, this square of cells, and also the state that I'm looking at. I could repeatedly refer to like cell of XY, but storing it in this std array is easier. And then I want to sort the cells based on their states, because I want to see which ones are black and which ones are unknown if they are. The easiest thing for me to do was just to sort them, but this assumes that I know whether the unknown enum value is less than black or not. I've defined it to be less than black, but if someone changes my code, I would like this to fail to compile. So I'm using the C++OX static assert. This will kill my compilation with a nice compiler error if this is false, and if so, it will print out. So I static assert that unknown is less than black, and if for some reason that's not true, it's going to say, hey, this code assumes that unknown is less than black. So afterwards, I can safely assume that they occur in this order. I'm going to use the STL sort function to sort my array according to the states. So I provide a lambda function here that will compare 2 states and compare 2 XY states and access their state field, and then return whether one is less than another. So after this, I know that it's sorted according to the values of the enum. I know that unknown must be less than black. So I can very easily ask, if this is a square of 3 black and 1 unknown cells, then I know that this unknown cell A0 must be white. Or if I have two unknown and two black cells, then I want to do that unreachable analysis that I talked about. So because I have to imagine one cell is black and see if the other one's unreachable, and then do vice versa, imagine the other cell is black and see if the first one's unreachable, I am going to use a for loop where I count up to 2 and then I'm going to swap at the end. I imagine cell A0 to be black, and then I see if that makes A1 unreachable. So I'm calling the same function here, but now it has an additional argument, imagine black. This is a set of coordinates that unreachable analysis will not step onto. And then it's going to swap and go vice versa. So this could prove some cells to be white. And then we're going to print out whitened cells to prevent pools. And so that's what's going on here. Not only do I detect these elbows of 3 cells and whiten over here, but I also detect this configuration and prove that this cell must be white. And then I find complete islands and go on. So that's unreachable analysis. Let me look real quickly here at how it works. Here's unreachable analysis. There's a big comment here. Now, usually when I'm writing code, I don't like big comments. I believe the code should explain what it's doing as part of its structure. If you have to write a comment, you're probably explaining something that is not obvious from the code, which means that either the code is too complicated or you're doing something that's inherently complicated. In this case, I'm using a little more exhaustive comments than usual because I'm expecting it to be read in depth by people who aren't experts in this area. But the analysis that I'm doing here is legitimately complicated. I'm doing a breadth first search. So this comment is explaining how unreachable analysis works. And in fact, I linked to the Wikipedia article about breadth first search if you're not familiar with it. So I assume that I'm starting with an unknown cell. And what this algorithm is doing is it's going to start with a cell. And it's going to imagine what would happen if it were white and see if it could find a path. In fact, the shortest path. And let me draw that configuration again. 2, got the 2. And we proved that this one is black. And this is the root. So imagine that we're looking at this root cell here. We've been given an X root and a Y root to ask, is this unreachable? And then a potential set saying, imagine that some other cell is black. In this case, in the first form of unreachable analysis, this set is empty, so we can ignore it for now. So according to the breadth first search, we use a queue of things to process. And we're going to push in a tuple. This is just a pair with 3 elements with the X root and Y root coordinates and the number of cells that we have consumed so far. So when we're starting our walk and trying to find a cell to meet up with, we've consumed 1 cell that would have been white. So that's why we've got a 1 there. And then we're going to remember which cells that we've seen so we don't go into circles. And so we're going to insert into the discovered set the root that we started with. Then we're going to process as long as this queue is empty. Queue is, what it is it's a container adapter. It's actually an interface over an STL container which provides storage. In this case, the container adapters can be backed by some set of vector, deck, and list. And with queue, it can be backed by either deck or list. Because what a queue does is you insert elements at one end and take them out of the other. Vector can't support that efficiently. It supports efficient pushback and popback, but nothing at the front. Whereas with deck and list, it does support this efficiently. The default with queue is to be backed by a deck, and that's exactly what I want. It's fine. So I don't need to customize this. So as long as the queue is not empty, I have nodes or cells to process. So I'm going to retrieve the front of the queue and pop it off, and I'm just going to give them names, X-cur, Y-cur, and N-cur. So what this is X-cur, Y-cur, and N-cur are the cell that I'm currently considering. For example, I could have found some long path. I started at the root over here. I was imagining that I would take some long path, and then I found this cur cell here, and maybe I needed to spend 8 cells to get there. So that's what these values are. What I need to do is see if I'm meeting up with a white or numbered region, because I'm trying to see, could this cell ever be white? So I need to look at what surrounds X-cur and Y-cur. And I need to know, are these regions white or numbered? So I've got a helper function for valid neighbors that for every valid neighbor, meaning neighbors that are orthogonal and not off the bounds of the grid, I am going to look at the regions that its neighbors belong to. If it's white, insert it into the set of white regions. If it's numbered, insert the set of numbered regions. Then I'm going to total up the number of cells that would be produced, the size of the region that would be produced. So imagine that I've got a cell over here, and it's going, and it finds a cell here. This is the Kerr cell, and it's bordering a region here that's marked maybe with a 10, and it's bordering here a white region that is of size 2. I want to know, can I consume Kerr? Can I step on it? I can if adding all of these white cells, plus the 2 white cells here, plus the 10 cells that are already in this number, will produce a number that is exactly equal to or less than 10. If it's too big, then I know that because I took the shortest path to get here, I can't legitimately step on Kerr. So I would remove it from consideration and not step there. So that's what I'm doing here. I'm going to total up the size of the white regions and numbered regions, and note that I'm doing this in a separate pass. It's important to do this because imagine that when I was discovering the neighbors of Kerr, I simply summed up the sizes right then and there. I could say, oh, look, here's a white region of size, this is a white region of size 4, and actually let me make this number bigger. Imagine that I found a white region of size 8 and another white region of size 8 here. I can't add these up without knowing whether they are the same region, because they could connect like this. So it's best for me to accumulate all of the regions, and because remember that this is a set and it enforces uniqueness, when I find duplicate regions, they're going to have the same shared Twitter value. So the set will enforce uniqueness, and then I can sum of just the unique white regions and numbered regions. And then I can start asking, is it okay for me to step on this cell? If stepping on Kerr would join 2 numbered regions, definitely prohibited. So I continue here. This is what implements what I call forbidden bridge analysis. If I stepped on this cell, it would be adjacent to 2 numbered regions, so it's got to be black. That's what's being handled for me. If I am going to meet up with a numbered region, that's potentially good, because I want to find a numbered region, but I can't make it too big. So I need to find its number and then see if all the cells that I consumed, plus the cells that are already in that region, if that's less than or equal to the number, great. We found a numbered region. We are reachable, so we return false from unreachable. If it's too big, though, we can't step there, so we continue. Whenever I execute continue here, I'm going to loop and continue processing the queue, and I'm going to drop whatever node I was considering on the floor, because I can't step on Kerr. So that's what continue means. Finally, if I have no numbered regions, but I've met up with a white region, I might be good, because I'm going to hope that that white region that I can connect to can itself be connected to a number. But there's a trick that I can do. Imagine that I am trying to find, I started from the root, and I got to the Kerr, and imagine that I spent 8 cells. And Kerr is bordering a white region. Say it's a bunch of cells. Say it's 12 cells. Okay. When I glue them together, I would have a white region of 20 cells. One of the things that I can ask is I can look at all of the numbers. I don't know which number this could possibly connect to, but I want to know that it can at least connect to one of them. So if these 20 cells plus another cell, because I would need to spend one more cell to connect at a minimum to another number, plus any of the numbers here, the size of the current region, if that's bigger than the number, then I'm an impossibly big white region. In this case, if I ever found a chunk of 20 white cells and the biggest number is 7, that's impossibly big. So my impossibly big white region helper will run through all of the regions and see if this number of white cells is impossibly big or not. If it is, I can't step on Kerr, I continue. Otherwise, I met up with a white region, so my cell is probably reachable. In this case, I'm only going to return that I'm unreachable if I'm absolutely certain. So when I return false here, I'm saying that I think this is reachable. It might not be, but I'm going to play it safe and allow the cell to remain unknown for the time being. Then, assuming I get this far, I believe that I can step on Kerr. So I'm going to essentially recurse, although this is iterating. And for the valid neighbors of Kerr, if the cell is unknown and I haven't already stepped on it, then I want to continue processing it. So I push it into my queue, its x and y coordinates, and because I'm stepping on a new cell, I need to increment mkerr by 1, and that's what I'm doing here. So this implements a breadth-first search. Again, read the Wikipedia article. It's going to try to find the shortest path, and when I start here, it's going to say, okay, here's the root. I've consumed a cell. Can I step here? Yes, I can. I've consumed 2 cells. Can I step here, though? Uh-oh, I can't. I'm too big. So it's going to remove this one from consideration. Same here, and it's going to find, oh, this root is unreachable. And when we get to the end of this function, if we found no way to meet up with a numbered region or a right region, we're unreachable, and we return true. And then I'll mark the cell as black. So that is one of my more advanced forms of analysis. There's an even more complicated one called confinement. What that does is ask, if the cell were either white or black, would I confine a region down so that if it's numbered, it can't consume the number of cells that's marked on? Or if it's white, it can't meet up with a numbered region, or if it's black, it can't consume m total black cells. This is a very powerful form of analysis, and it involves a whole lot of processing. Now that you've seen some of the simpler ones, I encourage you to read through the program and figure out how it works. And then finally, what solve does is if it's made as much progress as possible, it resorts to single guessing. It'll guess if a particular individual cell is white or black. What it will do is it will copy the grid, make a clean copy of the state, mark that cell as white or black to guess, run all of the analysis that it can, and see if it meets up with a contradiction. This is the only way that I know how to solve Wikipedia's example. Now, that might be my limitation as a human. Perhaps there's a better way to solve the Wikipedia example that doesn't involve the single guessing. If so, you could implement that in the solver, make it more efficient and simpler. And then there are functions to maintain regions, to add new regions, to fuse regions together. That's some very interesting stuff there. So I have a homework problem for you. Read through the program and figure out what it's doing. In part 4, at the end of part 4, I had mentioned that I had thought of about 3 ways to increase the speed of this program. Now I'll tell you what they are and give you a homework problem to implement one, some, or all of them. So the first thing that I've noticed is, where is this program spending all of its time? Now it's running in about 86, 87 milliseconds, but harder puzzles could make it run longer, especially bigger puzzles. And I would be interested in making the program run faster. So if you profile the program, what I found is that it's spending most of its time in this confinement analysis. It does a lot of complicated processing. And in particular, what it's doing is it's constantly inserting cells into sets, coordinates, pair, int, that sort of thing. And it's spending a lot of time there. So the first thing that I would like to try is to rewrite confine to see if it could avoid using sets so much and instead use vector or something else potentially more efficient. So that's sort of the first approach that I would try to make the program more efficient. The second is that it's spending a lot of time allocating these nodes in the set. And in particular, whenever we allocate something with new and delete, we need to call malloc, which calls heap alloc, which takes a lock and enters the kernel and does all of that. We would like to avoid that as much as possible. So I believe that by using custom allocators, we could make this significantly more efficient. As a test, I tried using an allocator that did absolutely no locking. In this case, that's okay because the program is currently single-threaded. And it sped up the program to about 55 milliseconds from 86. That's a substantial improvement. So using custom allocators is sort of the second approach that I would take to make the program faster. And third, I had mentioned single-threaded, parallelizing. Because we have a two-dimensional grid and because we're analyzing cells and sometimes regions, we can run a lot of this analysis in parallel. I have a quad-core machine. Hopefully you do too, maybe even more cores. This is what I call, what is called an embarrassingly parallel problem. So by parallelizing this, we could speed it up by a factor of 4 or as many cores that there are in your machine. And all of these could play together. So I believe that it's possible to solve this 6x, maybe even 10x faster than I currently am. So try out one of these approaches or construct your own hypothesis as to how to make the program faster, implement it, and report in the comments what you find. Thanks for watching.